Here, we're given quadratic function. It is provided in general form. So general form, ax squared plus bx plus c. So we want to know, does it have a max or a min? Quadratics will never have both. It'll have either a maximum or a minimum, and then what is it? You can look at the value of a, in this case it's 1, but more importantly it's positive. If a is positive, then the parabola would be opening up like that, and so you can see that this is going to have a minimum, not a maximum. Okay, then how can we get the value? We can graph it in the calculator and ask the calculator to give it to us. So you have to be able to graph it and then do the second trace, the calculate minimum in this case, left bound, right bound, yada, yada, yada. So you have to know how to do that process. If you do it, they're giving us the point roughly 2.5 negative 3.25. So that is our vertex. Is that point 2.5 negative 3.25? The minimum value of the function will always be the y part of the vertex. Right, so they're asking what is the smallest value that this function will give us, right? We give it the x, that's the input. The smallest value it's going to spit back out is negative 3.25. So it's a similar idea here. This is the standard form. So we want to know, first off, does it have a max or a min? You look at the value of a. In this case, the a is negative. That means we have a parabola opening down, which means we have a maximum, right? So we're going to be looking for the maximum. And then what is it? Just like in the last example, the maximum is going to occur at the vertex. In this form, we can see that the vertex is negative 7, 2, which tells us that the maximum value is that positive 2. Right. So we don't need to use the calculator in this case just because it was conveniently given to us in standard form, which means we can readily identify the vertex just from the equation. That's how we know the maximum is 2. If you graph this in your calculator and do second calculate maximum, it'll give you this point, and you say that the maximum value is that y value of 2. So the last couple examples were just finding the extreme values. Now we're going to use them to solve problems. This is we're going to do simple and not so simple problems. This one is a simple one because it is a word problem, but in general, you read through this. We've got a rocket being launched in the air. Its height, t seconds after it's launched, is given by this function. Find the maximum height it attains. This falls into the simple category because they're giving us the function. We just need to graph this and find the maximum. The difficult part of that is finding the correct window on your calculator that will fit this equation. But once you do that, you just do second calculate maximum. So I graphed it, I messed around with the window a little bit to the point that, again, when you graph it, you need to see the left bound, you need to see the maximum point, you need to see the right bound. Just because your calculator won't tell you this point unless you can see it on the screen. That's the only reason you need to make sure it's there. Once you get the point, you just need to be able to interpret what this is telling us, right? This vertex is at 23.4, 2909.6. It's asking for the maximum height. The maximum height, based on what the calculator is giving us, is this number, right? You have to understand that the y value is the height. Right, so find the maximum height the rocket attains. Maximum height is 2,909.6 meters. Then this number is the t. So that's telling us that it's attaining that maximum height 23.4 seconds after it takes off. That's all this number means. So questions like this could ask, how long after it takes off does it attain maximum height? That's this. It could ask, what is the maximum height? That's this. It could ask for both. When does it attain maximum height and what is the maximum height? And that's just a matter of making sure you're clear what the question is asking for. Now, this problem is not as simple. It's the same idea. We want to graph something in the calculator and use the calculator to find the maximum or minimum, right? but this one doesn't just give us a function, we have to come up with it. So we have 500 feet of fencing to fence in a rectangular area. What dimensions would give you max area? We have to be clear on what we know. We know we have 500 feet of fencing. We know it's in a rectangle. Right? That's it. That's really all that we know. So we've got some rectangle. We don't know the dimensions of the rectangle. We could choose to call it, well, I'll do blue, X and Y. Right? So what's in black, we know. What's in blue, we don't know. Right? We know it's a rectangle, so we had to decide what variables to use. The only other thing we know is that the perimeter is 500 feet. Okay? So we set up these variables, X and Y, the dimensions of our rectangle, and they're asking us to maximize area. Right? So the formula for area of a rectangle, length times width, that's X times Y. We can't put this in our calculator because it's got two variables. Calculator's only built to handle one variable. So we have to somehow rewrite this in terms of just X or just Y. That's where the perimeter comes in. We know the perimeter is 500 feet, and we know from the picture that that perimeter would be 2X plus 2Y. Right, so we could solve that equation for Y, for example. So we'd have 500 minus 2X is 2Y. So 250 minus X is Y. Right, now that can come over here and tell us that area is then X times 250 minus X. This we can type in our calculator, right? We couldn't do this because it had two variables, X and Y. This just has the one, just has X. So we can graph this and look for the maximum of this equation. So when we do that, got this. Again, you have to mess with the window a little bit to get it to work. I think I did 0 to 200 and 0 to 30,000. Right, got to see this. So it's giving us our point. And again, we just need to be clear what it's asking for. It's asking us for the dimensions. So it's telling us that X that we defined up above is 125 feet. It's telling us that max area is the 15,625 feet squared. Right? It's not asking us for the maximum area though, it's asking us for dimensions. If X is 125, then Y, we would use that equation there. Right? That would tell us that Y would also be 125 feet. So we know what the maximum area is, but that's not what's being asked for, just this part is. So this is, again, not a more complex problem than the last one, just because you had to come up with the equation on your own. Right, and you even needed to do a little substitution to get there. But once you've got the equation, you graph it, find the maximum, and you're done. Okay, this one, again, we want to be able to just graph something and call it a day, basically. So suppose that the price per unit in dollars of a cell phone production is modeled by this. So that's the price per unit in dollars, where X is in thousands of phones produced, and the revenue is represented by thousands of dollars, is R equals XP. Find the production level that will maximize revenue. So this one, similar to the last one, except a bit more information is given to us. Right? We have the price here, and we have revenue here. We're being asked to maximize revenue, which is this one. So we want to plug this in the calculator and find the maximum. Right, again, like in the last problem, we've got two variables, so we cannot plug this in the calculator. We need to cut it down to just one, but P is this, right? Which means we can just plug that in and say that revenue would look like this. Now we can plug this in the calculator and maximize it. So we've got this, right? We graphed this little guy, mess with the window enough, you find this parabola. The maximum is at 1,840,500. So again, we're just at the interpretation step. What do these numbers mean? What are they asking for? They're asking for the production level that will maximize revenue. So we're told that the production level is max, or the production level that maximizes revenue is when X is 1800. That max revenue is when the R is 40,500. So it's not asking for maximum revenue, which we would use this to get that. It's asking for the production level. So that's when X is 1800, but how is X measured? X is measured in thousands of phones produced. So it's this times 1,000. So you multiply by 1,000 and you say producing 1,800,000 phones would maximize revenue based on this information, right? If it had asked for maximum revenue, you could see, and you'd have to look, that R is also represented in thousands of dollars in that case. So the maximum revenue is 40,500,000, right? But again, that's not what it's asking for, just to highlight the fact that sometimes you do need to be clear how the variables are measured, right? Like maximum revenue isn't when you're producing 1,800 phones because X is measured in thousands of phones. It's when you're producing 1,800,000 phones. But that's all just coming into making sure you're reading the problem carefully and then making sure that you're answering whatever question or providing whatever they tell you to provide. And the last problem in this section, okay, this one isn't really an optimization problem as much as it is just a word problem that involves quadratics. So that's why I'm including it. But you've got a swimming pool, has a 12-inch border of sidewalk around its rectangular opening. The pool is 7 feet longer than it is wide, and the total area of the swimming pool and walkway is 98 square feet. What are the dimensions of the pool? So this is one where it could be somewhat difficult to draw everything that you're being told, right? But you've got a swimming pool, a rectangular swimming pool with a walkway around it. So like two little rectangles here. Then there's also the fact that it's a 12-inch border of sidewalk and then everything else is measured in feet. So you do need to be careful about that. What we've got now is we've got to define some variables. The pool is 7 feet longer than it is wide. So this is the width. This is the width plus 7, right? That's the length. Notice in blue, I am only giving the dimensions of the small rectangle inside. Right, so the big rectangle then would be like L plus 2, and this would be W plus 2. L and W are each measured in feet, right? But then the sidewalk is 12 inches, which is 1 foot. But then, like for this length right here, this side is L. Then you're adding 1 foot here, and you're adding 1 foot over here. So this total side here would be the length of the pool plus 2 feet. This would be the width of the pool plus 2 feet. We know that the total area of the swimming pool and walkway, so the area of the entire thing, is 98 square feet. Based on our picture, we can see that that area, length times width, would be L plus 2 times W plus 2. Okay, so 98 square feet is W plus 2 times L plus 2. But we know that L is really W plus 7. So 98 is W plus 2 times W plus 9, right? I wanted yellow. There. But that doesn't show up super well. Anyway, we're replacing L with W plus 7, so it's W plus 7 plus 2, W plus 9. So then we've got 0 equals W plus 2 times W plus 9 minus 98. You could go through and solve this algebraically. You could just graph it. So I've graphed it. You can see I just typed this in right here, just like it is into y1. I know that I'm looking for when it's equal to 0, right? I can tell there's going to be one of the zeros over here at some negative number, but since I'm looking for the width of a pool, I know that the negative number is irrelevant, so I use the calculator to just find this positive 0, which they tell me is 5. So I know that it's going to be what I want it to be when the width is 5 feet, which tells me that the length would have to be 12 feet, right? Because again, we know that the length is the width plus 7. Okay, we're asked what are the dimensions of the pool? 5 feet by 12 feet. You could check your answer by doing, you know the area should be 98 square feet for everything. So you could do 5 plus 2 times 12 plus 2. That should be 98, and it is. Right, so the area of the pool and walkway should be 98. It is, so those are the dimensions of this pool. Okay, so after going through this stuff, you should be comfortable finding extreme values of quadratic functions and then using that sort of process to solve the word problems we looked at, right? Some of the word problems probably seem more difficult, some seem less difficult, but you should be okay using this process to solve the problems we looked at.